Hey Tim, I wonder if you can differentiate exponential and log functions. Well, it turns out you can. And for y equals b to the x, y dash, that's the way of writing differential, that's dy dx, just a lot easier this way. You see the dash? That means the slope of y. Y dash equals some constant k times b to the x. So when you differentiate, the b to the x remains as b to the x. It actually doesn't change at all. This is a very unique function of exponents. And what is k? Well, it turns out that k is the slope of the graph y. There's my y equals 2 to the x. Turns out that it's the slope at x equals 0. And that is my constant there. It's the slope of that of the actual line at x equals 0. I hope that makes sense. Now, let's see. If I look at this graph, I see that y is bending upwards. And then I'm saying that y dash is very similar. It's also an exponent. It's also bending up. Let's see if that's true. So if y equals b to the x, and what we've just said is that y dash equals k, some constant, also b to the x. Now we can differentiate it again. We can say y double dash is equal to k. We take the constant out. K times differential of b to the x is k b to the x again. And so that's equal to k squared b to the x. But if we look carefully, we see that k squared is always positive and b to the x is always positive. You see my b to the x is always above the line. B to the x is always positive for all values of x. So what does that mean? Well, it means my y double dash is positive, therefore it's bending upwards. Okay, you're going to be looking out for a minimum value. So the two graphs, y equals 2 to the x, is going to be similar in shape to y dash, which is a constant times 2 to the x. So these graphs, as they increase, so their slopes increase also exponentially. Now let's introduce a special number called e. E is similar to pi. Pi is 3,41, and e equals 2,71818, etc., etc. So we said that if y equals b to the x, y dash equals y dash at 0 times b to the x. So it's a constant times b to the x. So y dash is the gradient of y at x equals 0. Let's look more closely and plot a couple of graphs of y equals 2 to the x. Y equals 2 to the x, y equals 2,5 to the x, and y equals 3 to the x. We're going to plot all three of those together. And let's look at the gradients at x equals 0. So there's y equals 3 to the x, y equals 2,5 to the x, and y equals 2 to the x. If we look at the gradients at x equals 0, you can see this one, the gradient is less than 1. Because why? Here, my change in x is 1, and my change in y is, it's about 0,7 or 0,8. So it's less than 1. My gradient is less than 1. If we look at y equals 2,5 to the x, we'll see a slightly different graph, and surprisingly we're not sure where that's going to go. It's very close to 1 at 2,5. Y equals 2,5 to the x. And if we look at the gradient at y equals 3 to the x, we see it's definitely higher than 1. You can see there, the slope is, the change in y is bigger than 1 for a change in x of 1. So let's look at it more closely. Let's now zoom in. So now I'm only going up to x equals 0,1. If we look at the y equals 2 to the x, see it's almost a straight line now. And you can see that m is definitely less than 1. Okay, because the increase here is 0,1 and the increase here is 0,1. So it's 0,08, 0,07 divided by 0,1. That's my m, less than 1. If we look at the y equals 2 to the 5, you can see it's also just less than 1, and 3 to the x is definitely more than 1. So there is a number between 2,5 and 3, where if it was y equals that number to the x, the gradient would be exactly 1. And that number, it turns out, is e. So there is a number, e, between 2, 5 and 3, where the gradient at x equals 0 is exactly 1. And therefore, there's a very important property now, that you can say that if y equals e to the x, which is 2,71 to the x, then y dash equals k, which is 1 now, times e to the x. So the differential is actually the same as the function. And it goes on, because if y equals e to the x, then y dash is equal to the e to the x. And if we differentiate it again, y double dash is equal to x, and so it goes. Now, e is an irrational number. What does that mean? It means you cannot express it as an integer divided by another integer. And a better way of saying that, I find, is to say we actually don't know what the number is. We keep on computing it, we compute, but we never find it. We go around the whole earth looking for more numbers. So it's not, so it's irrational. We don't know the value. Incidentally, if you have recurring fractions, one would think, well, those are also irrational because they go on forever. The difference is with a recurring decimal, you actually do know the value. You know that it's 0.666 forever. So it's actually rational and can in fact be expressed as an integer divided by an integer. That's been done previously. So how do we differentiate with the form e to the x? As with polynomials or any other function, we can use the chain rule. So just to recap, the chain rule says dy dx, the slope of y with respect to x, is equal to dy du times du dx. So this is only useful when we can find some other u that we can express y in terms of. Let's do a little example, just to recap. So I have a polynomial here. I have y equals 2x to the 3 plus 4x to the 4, and I want to differentiate it. So y dash is equal to, what is u? That's my inner function. So u, I can spot here. There's a nice inner function there, 2x to the 3 plus 4x. So y dash equals dy du. Well, u to the 4 becomes 4u to the 3. I just kept u in terms of all the x's there. So 4u to the 3 times u dash. Now you must differentiate what's the inner function. And it becomes, bring the 3 down, 3 times 2 gives you 6x squared plus 4. Okay, x to the 1 comes to the front. There's no more x. So there we have an example that we've done before where we're using the chain rule. So the chain rule is basically you express y as an outer function, you differentiate the outer function, and then you differentiate the inner function and multiply the two. Now we can apply this to e to the x as well. In fact, you can apply it to any function. Differentiation is easy. So if I had y equals e to the minus x squared, my outer function is e to the u. Okay, you see the e to the u. And my inner function, the function inside, is minus x squared. So if I differentiate e to the u, what do you get? E to the u. That's it. So easy. So e to the minus x squared remains as e to the minus x squared. Now I differentiate my u part, which is minus 2x, and I multiply the 2. And that's how easy it is. So differentiating e to the x is very simple. Now similarly, if y dash is equal to e to the x, then what is y? Well, just integrate e to the x, and you get e to the x again. They don't change. If the differential is e to the x, then surely the integral is also e to the x. But don't forget, there's also a constant, because we don't know what the interval is of my integration here. It's an indefinite integral. And also, what we learned with polynomials is we integrate, when you integrate a function to the ax plus b, okay, just need to put 1 over a in front and forget about the ax plus b. Treat him as a big X. So we have then, put 1 over a in front, and it's e to the big X, ax plus b. And don't forget your k again. So the same rules apply for finding equations of tangents, stationary points, and min-max, which you've learned with differentiation of polynomials. Just while I'm here, let's look at this little polynomial again. Just a little tip here. you must use the chain rule in a case like this. They will set the exam so that it's just possible to times all of these out and differentiate each term separately. They're not going to say 2x to the 3 plus 4x to the 16, because then you know, I can't multiply that out. It's going to end up with so many terms, it's going to take me a day to work out. They'll give you something that's just tempting to multiply out. Don't resist that temptation. Always go use the chain rule. You need to be familiar with the chain rule. If you're not sure, then brush up on it. But you need to know, whoa, there's a u in there. I can make it 4 times u to the 3 and then differentiate the u. Okay. So here's an example. Find the equation of the tangent at x equals 2 for y equals x squared plus 2e to the 2x. Okay, it sounds like a complicated sum to me. So what is the equation of a tangent? The equation of a tangent is the line that kisses the curve. So let's say a curve looks something like that. The tangent is the line there that just touches the curve at the value you specified. So in this case, I said x equals 2. Okay. So there's a random curve, and there's my tangent. See, it just touches the line. Now, did they ask me for the slope of the curve? No. They want the equation of the tangent. Equation means y equals something. And in this case, obviously, it's a straight line. So the form you're looking for is y equals mx plus c. And we've done this a couple of times. And it's the same principle whether you're using polynomials or sine, cos, or e to the x. So now we need to find the slope at that point. So we say, right, what's y dash? Well, looking at this function, y dash equals, bring the 2 down, okay, y equals 2x plus, the 2 remains there, from that one the 2 remains, and it's e to the 2x, that doesn't change, and we differentiate u inside here, okay, it's e to the u, so it's e to the 2x times 2 again, so it becomes y dash equals 2x plus 4e to the 2x. Now they asked us to find the equation of the tangent at x equals 2. So we put 2 into our y dash, and we get an expression for the slope at that point. Now the slope is my m in my equation here. So already I've got one of my 2 variables that I'm looking for. Remember, I'm not looking for x or y. I'm only looking for the equation of the tangent. So I'm looking for m and c. So where do we go from here? We've now found m. We need to know the coordinates of the point. So we know the x value is 2. So we're going to put the x value into the y expression, and we're going to find what is the actual coordinate. Now please don't put the x value into the y dash. Okay, we're not. That's not the right approach. We need to know what the coordinate is where these 2 graphs are passing through. So we put x into y, into the original y, and we find out that the point passes through x equals 2, y equals 4 plus 2e to the 4. You can easily put 2 into that equation, and you'll find y. Okay, now you can find c, because you know m, you know that this line passes through a point over there, where x is 2, and we know the y value as well. So y equals m times 2 plus c. And now we can work out c by rearranging the terms, and the equation of the tangent is then follows from there. I'd like to introduce the natural log, or ln x. If y equals e to the x, it means that x equals log of y base e. So we see how that e swivels. It's the base in the exponent, and it's also the base in the log. But whenever we have log of y base e, you write it simply as x equals ln y. So as soon as it's ln, it just means log base e. There's nothing else to it. It's similar to log 10. You just don't write the 10 as the base. Or rather log of y base 10. Okay, you don't write the 10, you just write it as log of y. Similarly, if it's a base e, you say ln of y. So for y equals ln x, then y dash is equal to 1 over x. So this is a property that I'm not going to prove. It's something that one needs to one needs to know this. Yeah, the differential of ln x is equal to 1 over x. So for example, if we have y equals ln 3x, then y dash, let's differentiate. So we have a u in the middle there. We have 3x is u. So the ln of u becomes 1 over u, which is 1 over 3x, times the differential of the 3x, which is simply 3. And then the 3's can cancel, and you're left with 1 over x. So we see how with all these differentials one can use the chain rule. Here's another example. Y equals ln and this big polynomial here. So y dash, this big polynomial is my u. So I've got ln of u, y dash equals 1 over u times the differential of u. And that you can simplify, or actually one can't simplify that any further. Here's another example. Y equals ln 2x plus 1 over 3x minus 1. Do you see that there's no u here? One would be tempted to put 2x plus 1 as a u, but then you can't express y fully as u, because 2x plus 1 as u, you can't. What about the 3x minus 1? You need to express y fully in terms of u. So this becomes difficult now. How are we going to do this? So there's no single u. So we need to manipulate this to get it into a usable format. You can remember that log of ab equals log of a plus log b. So y equals ln of 2x plus 1 over 3x minus 1 is simply ln of 2x plus 1 minus ln of 3x minus 1. And now we can easily differentiate these because we have a u here, 2x plus 1, and we have a u here, 3x minus 1. And that can be done quite simply. So you must always be on the lookout to simplify an expression before you jump in and do a more complicated operation. If the differential of ln is 1 over x, then surely the integral of 1 over x is ln x plus your indefinite integral constant. And this only applies for x is bigger than 0. So for example, find the area under the graph of y equals 1 over 3x minus 1 between 2 and 3. X is between 2 and 3. So the area is the integral from 2 to 3 of 1 over 3x minus 1, which becomes, okay, do you see the ax plus b, a being 3 and b being minus 1? So you keep him intact just as he is. You integrate 1 over big X. So it becomes ln. So it's ln of 3x minus 1, and you put 1 over a in front. Okay, and the integral from 2 to 3. So that reduces now to 1/3 times ln of 8 minus ln of 3, which is simply ln of 8 over 3, using our division property of logs. In the general form, okay, we might be asked to integrate, see here, y equals ln of x. It only works, it only has value for x is bigger than 0, where x is positive. But let's take, and this is now the graph of the reciprocal, y equals 1 over x. Okay, so the integral of 1 over x is ln x. But what about the integral of when x is negative of 1 over x? What we do there is we say, right, you can see that the area, say as an example there, we take that area, okay, it's exactly the same as if we took it on the other side of the x. And so the integral of 1 over x is simply ln of mod x plus k. So if you're asked to integrate the reciprocal in the negative zone, remember to put the mod in before you take logs. Otherwise your calculator is going to give you an error, and you don't want to get muddled up in the exam. So always take the mod, and then you can work out the area, whether x is negative or positive. There is an area, and it can be worked out using the mod function. So that's all from me on differentiating exponents and logs. Yeah, I think one needs to have a very clear understanding of the chain rule and know that when you differentiate e to the x in that form, it's e to the x, and when you differentiate log, it's 1 over x. and then using the chain rule with that, you can do some quite complex functions, and they reduce quite simply. Thanks very much, and feel free to ask questions, send me an email. If you have any sums that are bothering you, or you just want clarity on something, I'm more than happy to help. Thanks a lot. Ciao.